Okay, so now we're going to expand somewhat on what we've learned so far and just put basically the two parts together. Um, and we'll start with a simpler case, um, basically what's called a closed system. And what separates closed systems from what we're going to learn about here in a second, uh, from what's called a control volume, is that in a closed system, mass does not cross the boundary. So basically, you have a closed container, and mass does not come in or out. So basically, all the energy interactions come in the form of heat and work. Because you can have boundary work, right? You can shrink and expand the boundary, or you could have some other work input. But uh, bottom line is that the mass that you start with is going to be the same as the mass that you end with. All right, and so the general if you remember the general energy balance equation is simple. The change in the energy of the system's got to be related to the amount of energy that crosses the boundary coming in, and the difference between what came in and what left. Okay, so basically another way of putting that is that energy comes in. Some of it only has two choices. It either can hang out there or it can leave. So it's a very simple statement, but still very sort of powerful in its application. So the the change in the energy of the system, or the energy of the system, can come in three forms. They got the internal energy, the kinetic energy, and potential energy. And so the change in the energy of the system has to come about via changes in the internal energy, the kinetic energy, and the potential energy. And then energy can enter the system via heat and work. Because no mass is crossing the boundary, the mass term disappears. And likewise for energy leaving the system. So we have a simplified energy balance equation for closed systems. Okay, now for our purposes, uh, the change in kinetic energy and the change in the potential energy are almost always zero. So let's just think about what kinetic and potential energy are. Kinetic energy depends on the velocity of the system itself. So the change in kinetic energy of the system is related to how quickly the system is moving, and the change in potential energy um, is due to a change in position of the system. If the system isn't moving, if the system is stationary, uh, the change in kinetic energy equals the change in potential energy equals zero. All right, and that's almost always going to be the case for us. Okay, so in that case, the energy balance simplifies further to just the change in internal energy is equal to um, the heat and work coming in minus the heat and work leaving. And you can rearrange that however you want. So this is sort of the simplified energy balance. Uh, I guess I could say for stationary closed systems. All right, which is what we're going to be dealing with. All right, so that's it. And that's it for closed systems for the most part. I could rehash some of the stuff we've already done just to re-emphasize it. So there's some special quantities that we're going to need to deal with, uh, namely the boundary work, if you remember. And I'm just going to write the formulas for that. So the boundary work is the integral from the initial volume to the second, to the final volume of the pressure integrated over the volume. So you need pressure as a function of volume in order to calculate that integral. Okay. And most of the time, pressure is constant, or there's going to be some simplifying. There's going to be some simplifying assumptions available to you in order to calculate this integral, like constant pressure, or maybe I give you pressure as a function of volume immediately, or something to that effect. Okay, and then that's pretty much it. That's the only thing of any sort of special interest. I guess I could illustrate one point that if I have pressure as a function of volume, specific volume here, and I have two states, so I have state 1 and state 2. And here's one process. So I expand the system under a certain set of constraints, and then um, uh, compress the system via another set of constraints. I'll get two paths in the PV diagram. All right, so this is like, maybe this process here would be constant temperature. Maybe this pressure here would, or this this line here might be a, a a process by which, like, I insulate it. So it's not constant temperature, but maybe no heat is allowed to cross the boundary. But there's some difference between these two processes. And so now I can extract a net amount of work if I proceed between these two process between these two states via these two processes in a cycle like this. I can produce, every time I go around this cycle, I'll produce a certain amount of work. All right, so I can extract work by just cycling between these two states, but doing so under different processes. All right, so now we're just going to I want to do some examples.